Hi, welcome to topic number 12. In this lecture video, we're going to talk a little bit more about functions. Now, before I do that, I want to go back to topic number 11 and take a look at these pictures that I drew, these functions that I drew. So once again, to know this is a linear function is always a straight line. So when you see a straight line, that's a linear function. When you look at the equation part, right? When you look at the equation part of the function, all right, to the first power, that will be linear. Okay, a u is a quadratic function. When you look at the equation, when you see a square, right? When the highest exponent is a square, or the degree is the highest degree of a polynomial is a second power, then that's a quadratic function. Rational function involving with fractions. Okay, absolute value function has an absolute value symbol, which is give you a v. So when you see a v, that's an absolute value function. When you see absolute value sign, okay, then that's an absolute value function. All right, x to the third power, when the degree of the polynomial is third power, that's a cubic function. Then you got your two radical functions, a square root, right? If you see a square root function, the graph look like this. When you see a cube root function, the graph look like this. Okay, so that being said, let's take a look at more on functions. So we will come back to these two definition of concept for the domain of a rational function and square root function. So let's look at this one. So for this function, right, the highest exponent is a third power, so that is a cubic function, right? Because there's no square root, there's no absolute value, there's no square, there's not x to the first power, it's not a fraction being a rational function, so it's third power cubic function. All right, so if it's a cubic function, last time we said in topic 11, all the cubic function has the same domain. The graph will look something like this. Okay, domain is negative infinity to positive infinity. This one look a little bit different. Okay, the one that I drew you look like this, but this one doesn't quite look like that. And the reason is there's a negative sign right in front of the x to the third power. So in a future topic, we'll talk about something called a transformation of a function, which will actually show you how you can look at this equation part of the function to kind of approximately know what the function looks like. So let me graph this one, -4 plus 2x minus x to the third power. So your graph look like this way. It's actually coming down from the other way. Let me take a picture of it. All right, so as you can see, this arrow pointing up, also pointing left. This arrow, this part, keep on pointing down, also going right. So that means your x values on this function, okay, which is your domain, must be coming from negative infinity all the way to positive infinity. So your x values on this function exist from negative infinity to positive infinity. Okay, so if you don't believe me, we can go to the table, second graph, which is referring to the table. All right, you can go down, you can see x value keep on going. Okay, you can go back up. You can see the negative x value is keep on getting more negative. Okay. All right, the next one. All right, so you see this for this function, you see a square root right here. So that's a radical function. Specifically, it's a square root function. Because square root function look different than the cubic root function. All right, normally square root function looks like this way. Okay, but not in this particular example. I'm going to graph it here in a minute. So let's go back up here. To determine a domain of a square root function, okay, set what's inside the square root equal to 0 and solve for x. So once you solve for x, that answer tells you whether that's where the domain will begin or where it ends. All right, I will show you once I graph it. So I'm gonna set my negative x plus 3, so what's inside the radical, equal to 0, solve for x. If I move the negative x over, x equal to positive 3. All right, let me graph it so we can see exactly how this one look. So this one will look, this particular example is not going to look like this, because when I draw this back in topic 11, the x was positive. So this is a negative x. So like I said earlier, there's something there's things we can learn about looking at these equation part of the function to know to kind of know what the graph will look like. So square root of negative x plus 3. All right, I'm going to close my parenthesis. Okay, so if your graphing calculator does not have give you a little box, okay, so you can just enter negative x plus 3. Okay, make sure the cursor is outside of that box, outside the square root before you enter -2. So this time it's going that way, okay? It's actually going the other way. So this point right here, this point, the x value here got to be 3, okay? So this arrow, right? This arrow keep on pointing left, okay? So that means my x values, my domain, the x value exists from -infinity all the way to 3. 3 is actually a point on this function, so we will use a bracket. So there's nothing exists to the right-hand side of that 3. So if I go to my graph and go to tables, and you can see when x is greater than 3, all right, all the y value says error because your function does not exist there. Okay, so as you can see, when x equal to 3, right, that means substitute 3 for x, the y value is -2. So that means this point, right, in terms of a range, this point in terms of range is the lowest y value, is the lowest point on this graph, because the y value, right, if you look at the y value, as x keep on getting more negative, the y value gets bigger and bigger and bigger, right? All this y value gets bigger and bigger and bigger. So your range will actually start down to up, starting from -2, keep on going up to infinity. Okay, just going up real slowly. As you can see, the y value, each y value doesn't change much, right? So it is going up, just going up real slowly. So it might appear to be this is a flat line, but that's just the pixels. It's just going up real slowly. All right, this one is a rational function because I'm looking at this fraction bar right here. So that's a rational function. All right, so let me go back to that first page of your handout. All right, to determine the domain of a rational function, set the denominator not equal to 0, solve for x. So that's part of finding the restriction on the domain. Okay, so one restriction, my graph will divide into 2 parts. All right, let's go back there. So the first thing I'll do is set the denominator not equal to 0 and find the restriction on the domain. So 2x minus 1 set not equal to 0. I'm going to move my -1 over. So that's 2x not equal to +1. Divide both sides by 2. My x cannot be a half. All right, so let me graph this function. So this one will look something like the one I showed you back in topic 11. Not quite exact the same one. So since I got 2 terms on top, 2 terms in the denominator, okay, I need a calculator to see this is 1 term over 1 term. So I need to put the both term on top in a parenthesis, x minus 4. Close parenthesis, then divided by, these two terms need to be in a parenthesis, 2x minus 1. All right, here we go. The graph look like this. Okay, so let me zoom in a little bit. So make this little pop out a little bit. So I'm gonna go to window. I'm gonna go from -5 to +5 on both x direction and the y direction. Make the graph pops out a little bit better. Okay, so this, as you can see, this scope went above the x-axis, okay? So what's happening here is even though this arrow keep on point is coming from left, the x value coming from left, as it approaches the restriction, x cannot be a half, right? As the x value approaches the half, the y value gets larger and larger. And the other side, on the other side of the half, right? Your x value is keep on going to the right. So right here, like, slightly bigger than a half, right? Maybe like 0.51. If you do a 0.51, the y value is actually real negative. So it's coming up from left to the right. It's coming up and keep on going to the right. So my domain got to be the x value got to be coming from -infinity approaching to half, but it cannot be half. That's a restriction. Jungian means or my answer, right? My graph is divided into two parts. Or on the other side of half, right? So I'm using a half as a reference because I can't, because there are infinite numbers slightly bigger than a half. So my x value is starting at half on the other side of the graph, on the other graph, or the other side of restriction, keep on going to the right. There you go. So I'm using parentheses for both half because those are my restrictions. All right, this is an interesting rational function. So if we go back talking about, when we go back, look at what we review in terms of a rational expression. The first thing we did back in when we talk about rational expression, let me see if I can find it. Uh, When we first review the rational expression, we talk about restriction on the domain first, right? And then the next thing we did was talking about numerator denominator must be one term over one term, so we can simplify in the rational expression. So we did a couple example of that. So here, whenever we see a rational expression, we always want to try to factor the numerator and denominator, see if anything can be factored out. So x minus 1, there's nothing to factor, okay, other than 1. So I will put it in the parenthesis to indicate I already factor out a 1. The denominator here, x squared minus 9. So the topic we review on factoring polynomials. Here I got two perfect square terms with a subtraction sign in the middle. So that must be difference of squares, right? A squared minus b squared equal to a plus b times a minus b. All right, so before x was ever squared, it must be x and x. Before 9 was ever squared, it must be 3 and 3. One positive, one negative. All right. Set the denominator not equal to 0 and solve for x. So I know the x minus 3 can cancel out. I'm going to do that just in a minute, okay? I'm going to set each denominator that I factor not equal to 0. Solve for x. So move the positive 3 over to the right. Move the negative 3 over. Okay, one of my x cannot be -3. The other x cannot be +3. All right, so here are my two restrictions. So I know that x minus 3 can cancel out, right? So whenever factors get canceled out, in a rational expression or rational function, it actually creates a hole in the graph. So the x minus 3 canceled out, right? So this x minus 3 got canceled out. So x cannot be 3. So this is where the hole occurs. The hole is actually occurring at x equal to 3. Okay, so I do have two restrictions. So my graph is split into 3 parts. We cannot really see this hole, okay, in the graphing calculator. Let me go back to standard window, zoom number 6. Let me go back. So I'm always gonna graph the original function, okay? So that's x minus 3 divided by, oh, this is x squared minus 9. Can't really see the hole, okay? So it looked like it stops here. It doesn't. It actually keep going. So I'm gonna zoom in back in a little bit, go from -5 to +5. In my window. See, it's actually keep going. It's actually right hovering right above the x-axis. You know what? Let me sketch this one. All right. 1, 2, 3. 1, 2, 3, 4. Okay. So the left side, all right, the graph exists. This part right here, 1, 2, 3. So my graph, use a different color, use this one. 1, 2, 3. My function exists right here. Right? On the other side of -3, my function look like this. And then once I reach 3, there's a hole there. And then keep going. All right, so your domain coming from -infinity, right? Very, very left, approaching to the first restriction, which is -3, right? Then the graph pick up from the right-hand side of -3, approaching the next restriction, which is +3, okay? So this 3 is the hole, okay? The -3 is I call something else later on. Union, and then from 3 on the other side, on the right side of 3, keep on going to the right. All right. So this is looking at the functions, okay, and determine your domain. So in your own word, when factors cancel out in a function, what does it create in the graph? It actually creates what? A hole in the graph. Okay. Now, the next learning objective is about finding a domain and range of a function by looking at the graph. Okay, so this graph right here, real interesting. We'll make it a little bit bigger. Okay, this is called a piecewise function. This entire graph is made out of 2 different functions. So let's look at the domain. This arrow I know is pointing left, right? And then this arrow is pointing to the right. Okay, no problem. So your domain from left to the right, -infinity all the way to +infinity. But the range is a little bit different here. Okay, the range, this arrow is pointing down, right? But when it comes from left to the right, your y values are very negative until this point. At this particular point forward, the y value stays the same. So the y value here at that point is actually -1. So my range, technically, my y value down to up is actually coming from -infinity all the way up to -1. Because once it reaches -1, it stays horizontal. Remember when we review horizontal line, all the y values are the same, right? Now, in this case, it's -1 using brackets. Okay. Now, this one is a parabola. Okay. So, back in topic number 11, we said all the vertical parabola. Okay. This side is pointing left. This side is the x value keep on going right. All the vertical parabola domain is the same, -infinity to +infinity. The ranges was different from one parabola to the next. Since this parabola opens up, it creates a very bottom point. So at this very bottom point, the y value is actually 0, right? Because on the x-axis, all the y values are 0. So your range down to up, okay, is actually starting at 0 using bracket because it's actually on the line all the way to infinity. Okay, so this is looking at graphs to determine domain and range. Now, the next objective is what we call determine whether the graph is a function or not a function. Okay, we know we talked about this back in topic 11. We said that for a relation to be a function, there can be you cannot have the same x value. The only graph that has the same x value is a vertical line. So that's why we're going to use vertical line to test it out. Because vertical line, all the x values are the same. All right, so this is called the vertical line test. So if the vertical line cross my graph more than once, that means I'm going to have more than one same x value, then it's not a function. So looking at this circle graph, right? If I draw a vertical line through it, at this point and this point, the two x values are exactly the same. So that's not a function. All right, straight line is a linear function, so it is a function because a vertical line test only crosses one time. All right, ellipse, draw a vertical line through it. These 2 points, right? Got two of the same x value, not a function. Horizontal line is a function. It's actually called a constant function later on. So if we go back to what we reviewed a long time ago about polynomial, topic number 4. See, constant term is a last term without the variable, right? So if you see an equation says y equal to just a number, it's considered as a what? A constant function. Horizontal line is a constant function. All right, this is a vertical parabola, but this one is pointing down. So if I draw a vertical line through it, it will only cross this one time. So yes, parabola point down is a function. All right, parabola open left or open right is called the horizontal parabola. Parabola is not a function because the vertical line crosses 2 times. Not a function. Okay. Now the next objective is determine whether the relation representing a function. So right now I start you out with the equation. Okay, we're gonna solve for the variable y, and see if that y equal representing that y equal represent y as a function of x. Okay, so right now I don't know quite exactly what this is. So let's solve for the variable y. So my variable term is negative, so I'm going to move it over. So that should give me x equals positive 7y to the third. To get y by itself, I will need to divide both sides by 7. When I divide both sides by 7, this is 1x over 7, which I can rewrite it as 1 over 7x equal to y to the third. So just like we mentioned before, okay, when we talk about the exponent rules, topic number 3, squares and square roots are opposite operation. So they cancel each other out. So right now I have y to the third power. So to get rid of this y to get rid of this third power, what I can do is take a cube root on both sides, because cube and cube root cancels out. So my answer, y, is equal to cube roots of 1/7x, right? So right away, this is a what? A radical function. To be more specific, it's a cube root function. All right, so cube root function, back to topic number 11, cube root function look like this. Okay, so mine will look something like this, similar to this. So my domain, negative infinity to positive infinity. Determine the relation representing as a function of x. Yes. So yes. Y is a function of x. To be more specific than the type of function, is called a radical function. Or a cube root function. There you go. All right, now the next example is interesting. Okay, so this relation, this equation, right? We're gonna solve for the variable y. My y is trapped between two different terms. So I'm gonna show you this very powerful technique. It's called a cross product. Cross product is a very old-timey technique. You know, a lot of students learned this before. Okay, cross product says for any real number a, b, c, and d, if you have a over b equal to c over d, which is you got two term equal to, which means you got two terms here, and then each term be equal to each other. And when they are written in a fraction form, what we can do is multiply them diagonally, right? We sing this when we learn about proportion. Multiply them diagonally, a times d is ad, then set it equal to, multiply the other two diagonally, b times c, which is bc. Okay, so whenever you see two fraction term, or if you see two term equal to each other, you can use this technique to solve for the variable. So this x right now is x over 1. So I'm going to multiply it diagonally. Okay, so I'm going to say 1 times 7y in positive 3. 1 times 7y is 7y. 1 times positive, because these got two terms here. This one going to multiply both terms. Is positive 3. Set it equal to, multiply it diagonally, x times these two terms down there. X times 5y is 5xy. X times negative 1 is negative x. Okay, so now I need to solve for the variable y. So my variable term is 7y and positive 5xy. Since both of them are positive, right? Doesn't matter which side you go, which side you want to move them to. I want to move the 7y to the right because that will force me to move the negative x back over to the left side. So I will have more positive term in this equation than negative terms. Okay, because if you move the 5xy to the left, move the 3 to the right, then you will have more negative term. Okay, move the 7y to the right, and I'm gonna move the negative x back to the left side. And I'm gonna put it right in front of the positive 3. So negative x come over, become positive. Still got positive 3 there. Equal to 5xy on the right, positive 7y come over, becomes negative. So now my two variable term is now on the same side, and I cannot combine these two terms because they're not like terms. So what do I do here? Okay, when my variable is trapped between two different terms and I cannot combine them. So this is where the factoring comes in, because if you think about it, the common factor between these two terms is the y. So if I factor out the y between these two terms, what's left will be 5x and negative 7. because by factoring, I'm making these two terms into a one single term, right? Now it's equal to x plus 3. Because I want the letter y in two different terms become one single letter y. So the only thing I can do is actually factor them out. So now y is a variable that will make 5x minus 7 the coefficient. So that's what I will divide on both sides. So my answer, y equals x plus 3 over 5x minus 7. So does y representing a function of x? Yes. Is a what? What kind of function is this one? Yes, it is a rational function, right? Because it's a fraction. All right, so from the correct answer number 1, okay, I'm gonna set a denominator not equal to 0. So I'm gonna looking for the domain here. Find the restriction on the domain and set it not equal to 0, solve for x. So move my -7 over. So that's 5x cannot be 7 and divide both sides by 5. My x cannot be 7 over 5. So one restriction, okay, that means my graph is divided into two parts. I'm gonna scroll down a little bit. Yep, x plus 3 divided by 5x minus 7. Okay, this is what I'm gonna do standard window. So this is what my rational function looks like. There you go. So this arrow keep on going to the left. It's just hovering so close to the x-axis you can't even see it. Okay, it's real dark. All right, so one restriction to my graph is divided into two parts. So my domain got to be, my x value got to be coming from -infinity all the way to my restriction, 7 over 5, union, use parenthesis, cannot be, because my restriction was what x cannot be. Then my graph pick up on the other side of 7 over 5 and keep on going to the right. All right, let's take a look at some of the homework. How do you determine the domain of a square root function? So you can just enter in what I wrote on the lecture handouts from 1 and 2. To determine whether the relation represents y as a function of x, we got to solve for y. All right, question number 4. Okay, do the exactly same thing as I just did earlier, right? So tell me what type of function it is. Set the denominator not equal to 0. Okay, and solve for x, and then tell me what the domain is. All right, question number 5 is the same one, the one I just did. Solve for the variable y, okay, and follow the steps. Question number 6, okay, determine the range. So this one just one range. So I just show you, I just showed the same exact example earlier. So just enter the range for me. And this one right here, determine if the graph shows a relation or is a function or not a function. So you draw a vertical line through it. So it got to be a function because it only crosses one time. So this is a what? This is a cubic function, right? This graph looked just like this one. It's a cubic function. So it is a function. Okay. All right. So we talk a little bit more about function in this lecture video. We looked at the equation part of the function and then determine the domain. And then we look at the graph of a function and then determine the domain and the range. And then we talk about solving for y and see if the relation represent y as a function of x. Okay, thank you so much for watching.